Hey everybody, welcome to week 1 of PS231. It's kind of crazy, it's a little bit weird that we're doing it this way. Here we are. So you would have already watched one video from me, maybe. And hopefully it answered a lot of your questions or let you know not just, what the class is about or anything, but just sort of the general, I hate to use the word vibe, it's vibe, the vibe of the class. These videos is going to be, especially early on, before we get a chance to talk about political processes in a really deep sense. But so early on in this process, these videos, I hope that they don't come across as too sterile. So my goals for you in this class go beyond just teaching you some game theory. I think that one reason that it's great to learn game theory, even if you never do any more game theory in your life, is that it makes you a somewhat more disciplined thinker. It's not unique in that sense. There's all sorts of different ways to become a more disciplined thinker. But it's an especially useful way, I think. And one reason that game theory is so useful for helping you to become a more disciplined thinker is that it utilizes some powerful foundational tools from mathematics to take a huge, complicated reality, this empirical reality that we live in, this gigantic data-generating process that's all around us. I already feel like an idiot. We're 30 seconds into the first video and I'm doing this. This is very bad. But the world is big enough to warrant doing this. And complicated. So many different processes at work. And that's just the political end. So we have this big empirical world that we need to think disciplined thoughts about. We need to offer good causal explanations. We need to make predictions. Sometimes we need to measure a given concept. What is democracy? That's so hard, right? Just think about that for a second. That's so hard. So we have this big, complicated world that we need to think disciplined thoughts in. And it's so big and so complicated that we have to sort of turn it into something that we can work on. And that's a model. And in particular, in this class, we're going to be looking mostly at game-theoretic models, which are simple mathematical representations of a given strategic interaction, and then we're going to study that model. So after we've taken the big real reality, so once we've taken the big real reality, we need to take the big real reality and convert it into a mathematical object. And that mathematical object, this game-theoretic model, is going to be something that we can easily think disciplined thoughts about. And then we'll take what we've learned in the game-theoretic fable land, where we've been thinking nothing but disciplined thoughts, and then we'll go back to reality and say, well, does it look like our model and reality, did we learn something? Did we gain insight? Have we shed light on something? Does it make useful predictions? Does it give a compelling explanation? But implicit in all of this, the two worlds, all of this is like, any philosopher would be laughing their butt off at me, for the record. This is complicated and nuanced, and I'm trying to give you a very quick and dirty interpretation. But this is also what happens in mainstream political science, for the record. So these two worlds, the real reality, the complicated empirical reality, where it's very difficult to think disciplined thoughts, and the simple mathematical game-theoretic reality, where it's much more natural to think disciplined thoughts. How do we turn them into one another? What's the machine that takes one world and turns it into the other world? How do we encode the world? That's a powerful set of words. I'm going to say it again. How do we encode the world? How do we take the strategic contexts that we want to learn about, wars, elections, civil strife, trade, how do we take those important processes and encode them in such a context-independent way that you could train a computer to understand what you're doing? And that's what we're going to talk about today. Well, in order to get that process started, we need to just make sure we're all on the same footing in terms of the very, very basics of the mathematical apparatus. So our first lecture isn't going to be about how to study strategic actors in an interdependent setting. The first week is just going to be, hey, what are the basic tools that we use to then study those things later on in the class? So, in the A block of today's lecture, we're going to talk about basic elementary logic. What is a statement? How do we link statements together? How do we form an argument using statements? In the B block, we'll talk about sets, which are basically the simplest mathematical way to gather a bunch of things. I'm just begging the question left and right. To gather a bunch of things in a conceptually coherent way. You'll see what I mean, I swear. And then in the C block, we'll talk about functions, where the question becomes, how do we link one set to another set? So there's a function that takes every congressperson, the set of all people in the United States House of Representatives, and on any given vote that comes to the floor, there's a function that takes that set of people and spits out, did the voter in question vote yay on the proposal, nay on the proposal, or did they abstain? So in other words, we have two sets, the set of all Congress people and the set of yay, nay, abstain. And how do we link those two sets in this conceptually useful way? Well, through a simple function that you might say, the vote function, that reads in a congressperson and spits out a vote. So our goal for today is to have the basic processes of encoding the world under our fingers. And so as such, your problem set is going to be oriented around just making sure that you're ready to speak this language that will, at various points of the class, it will seem very unnatural to you, the language, but at other points in the class, it will seem quite natural to you, if your experience is anything like mine and a lot of other people's. So I want you to think about this it's not a math thing. Like we use the word math as such a stand-in for so many different neuroses that we have. It's not a math thing. This is a linguistic thing right now. We got to take our plain language interpretation of the world and convert it into a slightly more austere, less contextualized version of the world. So let's get started. So before I get started with the A block, I just wanted to recommend a book to you. So this was mentioned on the syllabus. The name of this, I feel like I'm a preschool teacher right now. The name of our book is Set, Functions, and Logic. And so I don't really have a mirror there. An Introduction to Abstract Mathematics, 3rd edition, by Keith Devlin, who is a mathematician, an author, sort of a mathematics advocate or ambassador. He works at Stanford. This is a great book. I don't say that lightly. So this book is very rare. In your high school mathematics classes, math was probably a way to think about how to compute things. So if I give you 4x equals 24, and already some of you are going, oh, it's okay, you're gonna be fine. So if I give you 4x equals 24, solve for x, then you get taught rules of computation, right? So you get told that, well, if there's a constant on both sides, subtract it away. We don't have that in this example. And then divide both sides of the equation, and then so you divide both sides by 4 and you end up with x equals 6. And so math is just a way to compute things. But if you've dipped your toe in any mathematical waters past that, you learn pretty quickly that real mathematics has nothing to do with computation. Computing things properly is super important. But there's a reason that we have calculators and computers and all this sort of stuff. It's not just how to compute things, it's also how to think, how to make arguments, how to develop a concept, how to measure. Now that transition from I'm a high school computational math person and I'm a college abstract argument style math person, that gap is a serious chasm, replete with pitfalls and moments of fear and all sorts of good reason to walk away from the process before you get deep enough to really know what's happening. And that's why this book is great. The reason that this book is great, I don't know which side to be on. So the reason that this book, who cares about me? Let's look at the book. The reason that this book is great, am I pointing at the book? The reason that this book is great is it helps you navigate that chasm. It helps you turn from a computational sort of person into an abstract argument sort of person. Better than any book I've ever seen. Consequently, I think that this is a useful book for anybody. Even if you're not going to be doing a whole lot of math or game theory for the rest of your life, this helps you to understand what's happening in math. And if you're ever going to become the sort of person, hypothetically, for whom math becomes a recreation, I know that seems odd to you, but for many people, mathematics is indeed something that can be done for fun. If you're ever going to become one of those people, which I hope you'll consider it, then you need to learn how to navigate that chasm between computational math and abstract math. So you should be able to find an inexpensive copy of this somewhere. Ordinarily, I say used copies and old editions are fine, but this is the third edition, and my understanding is that the third edition involved large structural departures from the previous two editions. And so, at the very least, if you do pick up an old copy, just make sure that it's somewhat comparable to what you'd find in the third. But highly, highly, highly recommended. You should be able to find it for not too much money. Certainly worth thinking about getting. So here in the A block, we're going to be talking about basic elementary logic. How do we make valid arguments? How do we turn assumptions into conclusions in a way that's reliable, that doesn't involve any slippage, that never breaks? Part of that implicitly means that in game theoretic analysis in the social sciences, and really any mathematical analysis, any purely theoretical analysis in the social sciences, we're concerned with some balance between internal consistency, sometimes called internal validity. Does the machine, is it self-contained, is it correct? Versus external validity, which is, does something generalize? So we worry quite a bit about making sure that whatever we tell you is true. Now, the things that we tell you in these fake mathematical fable worlds, they will be true, but they may not be especially relevant for something. So they might have high internal validity in the sense that they're true, they work. But they'll have low external validity sometimes in the sense that they don't generalize to any given case particularly well. Necessarily, by using logic, mathematical logic, by working at this abstract of a level, we're necessarily saying there's a certain amount of internal validity that we're going to require for something to constitute useful knowledge, right? I don't want to get too far into the weeds with this, but it is important to say to you explicitly that one reason that we do this is to make sure that we have high internal validity. So the most fundamental building block of elementary logic, like we'll be talking about, is the statement. That is the atom of all arguments, is the statement. A statement is a claim, an utterance, a piece of linguistic content. If we go any further into the weeds, we're going to have to become philosophers. So let's just keep things naive for now. That is either true or false, but not both, and not neither, right? So a statement is an unambiguous claim that can either be true or false, but not both. So here's an example of a statement. The United States of America is a democracy. Now, the idea there is that the United States is either a democracy or it is not. A country cannot simultaneously be a democracy and a non-democracy. You're either a democracy or you're not. Now, our definition of democracy then becomes somewhat ambiguous, right? So we don't want it to be the case that for me, the United States is a democracy, and for you, the United States is not a democracy. We want it to be the case that anybody that was reading the code that we're going to be using would come to the same conclusion. We don't want it to be the case that there's room for judgment on this sort of thing. So we want it to be the case that a mathematical statement has the same unique meaning every time, irrespective of context. So we don't want it to be the case that I say, in my personal context, the United States of America is a democracy, and you say, in your personal context, the United States of America is not a democracy. So we have left some wiggle room without a precise definition of what we mean by democracy. So if I wanted to refine my statement to make sure that it was drum tight, I would say the United States has a Polity 4 score of 10. A Polity 4 is just a data set that we use that identifies certain key features of the way that a country's regime works in any given year. Executive recruitment, are there free elections, blah, blah, blah. I'll put the website here so that you can peruse the Polity 4 project if you're so inclined. And the idea is it runs from -10 to 10. Actually, let me try that again so that I can do this from a more you-centered perspective. Every country is given a score somewhere between -10 and 10, where -10 means this country is an autocracy in the strongest sense per this scale, and a 10 means this country is a democracy in the strongest sense per this scale. And actually, the way that most people use polity scores in just a linguistic sense is to say, if a country has a polity score less than -7, so -7, -8, -9, or -10, that's an autocracy. And if they have a polity score of 7 or greater, 7, 8, 9, 10, then that's a democracy. And everything in between is mixed. Sometimes you hear the word anocracy. So if I wanted to be all the way drum tight, an example of a statement is the United States has a polity score of 10. Right? That is either true or false, but not both and not neither. Right? It has a polity score. It's a number. Every number is 10 or not 10. So we're good. That's a statement. Boom. No ambiguity. Independent of context. I'm spending some time on this because you don't realize how much our language, plain language, relies on context to increase efficiency. So, for example, consider the sentence, "The man saw the woman with the telescope." Okay, well now there are at least two potential interpretations of that. One is, in World 1, there's a man and there's a woman with a telescope, and the man sees the woman with the telescope. In World 2, there's a man with a telescope and a woman, presumably very far away. And the man sees, using the telescope, the woman. Now, that ambiguity is annoying in plain language, and it's doubly annoying in mathematical language. That level of ambiguity means that we can't really deliver the sort of internal validity that we're looking for. So that's what we're trying to get rid of by using these mathematical statements. Now, of course, it's possible to go too far with this, and in terms of good practice or good decorum or just being a good scholar, if I said to you, the United States is a democracy, you could well say, well, that's contextual, and what I think is a democracy isn't the same as what you think is a democracy. In which case, my answer would be, yeah, but I could think up a reasonable definition for a democracy that we'd be able to agree on, and it's true or it's false, but not both and not neither. Now, we might bicker about what the right measure is, but as long as it's sort of a solvable problem rather than a solved problem, that's usually the criterion in question. This ability to use context to imbue a versatile word with meaning, like I or today, is called indexicality. This indexicality, this context of language, it's what makes plain language such a joy to use, because otherwise we'd have to explain so much every time. So, is a small elephant smaller than a large ant? No, presumably the large ant is large with respect to other ants, and the small elephant is small with respect to other elephants, but the smallest elephant is bigger than the largest ant, right? So that indexicality, I don't want to have to explain this every time I want to talk about elephants and ants, which apparently is all the time. I don't want to have to do that. That's annoying. So we don't want to. That indexicality is great for plain language. It's why it's easy for us to talk to one another. It's the reason that I can use the pronoun I and mean me, a person with social security number, right? And you can use that same word, I, and you don't mean me with my social security number. You mean you. But when I say you, I mean you. So the same word, the same one-letter word, I, can mean something different, because for each of the billions and billions of people that could say that word, it means a completely different thing. When you think about it, the one letter I in the English language can mean a different thing for each of the billions and billions of different people in the world. How efficient is that? It can mean a bunch of different things. It can mean billions of different things. That's really cool, right? Yeah. See what I'm saying? A computer would get very angry right now. It wants to know that Rob is Rob, right? It wants to know that Sang-hoon is Sang-hoon. It wants to know that Chancellor Jones is Chancellor Jones. It doesn't want to use the word I and have to keep track of who is doing the talking and therefore who is the first person in the sentence. We don't want it to be the case that context matters when we issue a logical statement. A logical statement has to be something where it is obvious who the speaker is. It is obvious what the time is, so that the word I is of no use, and the word today is of no use. A logical statement is an utterance, a claim. I'm going to avoid a whole lot of philosophical problems and just say that that's enough. Technically speaking, I'm really begging the question, right? So I've got this claim that is unambiguously true or false, but not both and not neither. So that's what a statement is. Statements alone aren't very interesting. What's interesting is how we can connect them to make other statements, right? So can I take two or more statements and some operator that takes them and spits out another statement? And that's what we're going to talk about, is a couple of those. If we're going to use this for anything, if this machine is going to be anything more interesting than a bunch of single-celled logical organisms, if we're going to build multi-celled organisms using statements, if we're going to combine them, we're going to combine them, right? We need to know what combining them looks like. Now, what's nice is, at the level of statements, these all have well-established plain language interpretations that then we'll have to clean some of the context out. But this at least should be pretty intuitive. So, how are we going to combine statements in a meaningful way? Well, it's going to be easier if we go to the board for that. So, zink, a zink, a zink. And there we are. Now we've got a whole space to work on. That's pretty cool. Okay, so let's talk about how to combine statements. And in order to do that, I'm going to use a device called a truth table. Truth tables are actually a reasonable way to construct an entire logical argument if it's a simple sort of thing. But I think that these are just super useful ways to introduce some of these main operators, these main ways to turn two statements into a new statement. So the first thing that we do when we make a truth table is we write out all the possible combinations of truth and falsehood of our core statements in question. So let's not beat around the bush. So let's say that I've got two statements. We'll call them P and Q. And P is going to be the United States is a democracy. That's unambiguously true or false once we've defined what a democracy is with respect to a Polity score or something like that. And let's say the Q is Canada is a democracy. So I've got two statements which, with appropriate definitions, are unambiguous. These are good, clean claims. And I can write out all the combinations of them. And it turns out that there are four combinations of truth or falsehood of those two claims. Let's think about it. So I'll make a column that's P, and I'll make a column that's Q. Okay, so in the P column, I'll say that P could be false, false, true, true. And then in the Q column, I'll have false, true, false, true. So I've got four combinations. These combinations of truth or falsehood of the constituent statements are called cases. So each row in this truth table is a case. Case 1, case 2, case 3, case 4. The reason that you can't go too far with truth tables is that the number of rows in a truth table will be 2 to the number of statements that you're trying to combine, right? So if I was combining 3 statements, I would need 8 rows. 4 statements, 16. 5 statements, 32, and so on. I have trouble keeping track of a grocery list, much less a 128-row truth table, so let's try to keep things easy on your old professor. Okay, so I have all 4 combinations. Great. Now I'll be able to define new statements using operators where I know their truth value, the truth value of the new statement, based only on the truth value of P and Q. So let's think about the easiest way to combine 2 statements into a new statement. If I was just speaking in plain language, I might say the following to you. The United States is a democracy, and Canada is a democracy. So the P part is in there, the United States is a democracy, and the Q part is in there, Canada is a democracy. all that I've done to make this new statement is put an and in there. Now, mathematically, and involves this little wedge symbol, okay? But whenever I write that wedge symbol, I really just mean and. Now, think about what it means in plain language. What would it take for me to be right if I said that? So if I said to you, the United States is a democracy and Canada is a democracy, and you're like, I'm the fact checker, and I'm going to check to see if that statement is true. Well, what would make me right if both P was true and Q was true? And what would make me wrong? Anything else, right? Because in case 1, they're both false. That leads to a false. In case 2, P is false and Q is true. Well, I needed them both, so I'm wrong. That's still a false. In case 3, P is true and Q is false. I needed them both. I'm still wrong. Only in case 4, where they're both true, am I correct when I say P and Q. So when you think about it, now I've made a whole new column in my truth table, and I know everything there is to know about the statement P and Q, so long as I know what I need to know from P and Q separately, right? So if you know about P and you know about Q, then you know about P and Q. We just combined a statement to make a new statement, and what's more, we know the truth value of this new statement depending on what we know about the core statements. Well, now you're thinking to yourself, well, I know other words that seem like the word and. Do they have logical equivalence? And, well, if you were thinking about or, then yeah. Okay, so the symbol for or in basic logic like this is a V. So just take that wedge and turn it upside down. And that reads P or Q. Now, whereas and is pretty unambiguous, if you're the fact checker, you know exactly what to check. If I said to you, the United States is a democracy or Canada is a democracy, there's some ambiguity in that plain language sentence, right? The reason for that ambiguity is that you don't know if I mean that precisely one is true and thus not both, or at least one is true. So this is a chance for us to have a formal definition of the word or. And in most mathematical applications, and including here, whenever we say or, we mean implicitly or both is always allowed. So just to work through that, in case 1 of our truth table, both P and Q are false, which means that there's no confusion there. That's a false. Case 2, well, P is false but Q is true. I only needed one to be true. I have one that's true. I did it. That's true. Case 3, same thing but for P instead of Q. P is true. I only needed one, so that's true. Finally, in case 4, this is what we were just talking about. Now they're both true. And our definition of or is going to be or both is baked in there. I'll try to say or both most of the time, but it's implicit. Or both is implicit. Every time that I don't mean or both, I will say but not both. So you can file that as a true. So now look, we made 2 new statements. We made P and Q, and we went false, 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 true, working top to bottom. And we made another statement, P or Q, that went false, true, 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 top to bottom. The third very standard way to make a new statement out of an old statement is to negate a statement. So here you don't even need 2. So if I wanted to say not P, negate P, what that means is if P is true, give me a false. And if P is false, give me a true. That symbol is just this little negation symbol. So I'm going to write it in the same truth table, but you could do this with a 2-row one if you wanted to. So not P goes down true, true, false, false. It just gives you the exact opposite. Where that's well defined because statements are only true or false, but not both. So turn a true to a false, turn a false to a true. And likewise, not Q, right? That goes true, false, true, false. And now if you were so inclined, you could make new statements using not P and not Q instead of P and Q. These are all just statements. A statement is just something that's true or false, but not both. That's it. And already it's so much easier, once you get used to it, I know, it's so much easier to think this way because a lot of those details that can be so confusing are out of the picture. Now, we've made some new statements using old statements with these and, or, and not operators. And that's great. But we haven't constructed any new knowledge, right? So when you think about what science is, whatever it means, we start from things that we think that we know. We start from things that we think are true, and then we make claims about other things that must be true if we were right about what we thought were true. In other words, if P is true, then Q is true. That's how you make an argument, right? You don't make an argument just from ands and ors and nots. You make arguments with ifs and thens. So we need to think about what conditionals look like. So I'm going to avoid, whenever I can, the use of the word implication because implication has a very loaded meaning. Instead, I'm going to say material conditional here, where that reads if P then Q. And the symbol that I'm going to use is this double arrow. And that reads if P then Q, or if you really want to say it, P implies Q. Now, let me just pause for a second because here's something that'll influence your plain language now that you've done 10 minutes of logic. So, in the claim, if P is true, then Q is true, in that argument, P is a sufficient condition for Q. If you knew that P were true, then you would also know that Q is true. And Q is a necessary condition for P. Anytime P is true, Q has to be true too. So sufficient conditions, that's the if part. P is sufficient for Q. And Q, that's the then part. Q is necessary for P. You'll have a chance to work on that on the problem set. So, I'm going to start at the bottom when I define this implication thing for you, this conditional thing, this double arrow, this if-then. So, what would make that statement false? When would you be irritated? So I view a conditional claim like this as a promise. And anytime I'm happy, or at the very least not angry, I put true. And anytime I'm angry, I put false. So when would I be angry? When would the fact checker be angry with somebody that said if P then Q? Well, they'd be angry if P were true and Q weren't. That's case 3. So in case 3, P is true and Q is false. And you promised me that if P was true, then Q would be true as well. So this is the test and you failed it. So in other words, in case 3, P implies Q is false. Conversely, in case 4, P is true and Q is also true. That's great. That's what you promised would happen. So I'm going to put a true there. That leaves cases 1 and 2. This is going to be a little confusing for some of you. If you've seen this before, it won't be confusing, but it was probably confusing the first time that you saw it too. So these top 2 cases, that's the world where P is false, where the sort of the if part of the statement isn't true. Well, would the fact checker be mad? No, they wouldn't be mad. So if I said to you, if you work hard and study, you will get a good grade in this class. When would you be mad at me? If you didn't study, you'd have no right to be mad at me because you didn't live up to the claim that I was talking about. You'd only be mad at me if you worked hard and you didn't get a good grade, right? So in these top 2 cases where P isn't true, we're still going to call that a true. Now, the true that you get in these top 2, where P was false, is the same exact true as what you got in case 4. But qualitatively, just on a human level, it doesn't quite feel right? So sometimes you see this referred to as vacuously true. So the implication if P then Q, this conditional result, if P then Q, that is vacuously true if P isn't true. So here's an example. I have won every marathon that I've ever run in record time. Every time I've run a marathon, I set a world record. That's true. That's a true statement. Why? Because I've run 0 marathons, obviously, right? So it is vacuously true that I've won every marathon I've ever run. It's also vacuously true that I've lost every marathon that I've ever run. So it's vacuously true. It's just something you'll learn to become comfortable with it, but that's sort of what's going on there. But the most important part, if I wanted to show you that if P then Q, I can assume that P is true, because if it weren't, then my claim would already be true vacuously. Let me repeat that. If I wanted to show you that if P then Q, if I wanted to prove that, I don't have to worry about the situations where P isn't true, because vacuously the if P then Q claim holds. Those top 2 rows are T's. So all that I need to show you in order for my claim to be correct is that every time that P is true, Q is true too. I'm just going to work out Q if Q then P, because I'm going to need it here for a second, and it's some good extra practice. So if Canada is a democracy, then the United States is a democracy. Okay, well, in case 1, Q is false, so the claim is vacuously true to begin with. In case 2, Q is true, but P is false. That's when you'd be mad, so that's a false. You understand? In case 3, Q is false, so we don't have to look anymore. Vacuously, the statement is true. And finally, in case 4, Q is true and P is true. That's exactly what we wanted to see, so that's a true. So now, we can assess the truth or falsehood of an if-then claim, which is like the foundation of something that sounds kind of like a hypothesis, right? We can assess the truth or falsehood of that sort of statement using only the constituent statements. Now, I want to introduce one final one right now, and it's called biconditional. It means if and only if. Here we're saying that 2 statements are actually fully equivalent to one another. So the idea here is that implication only tells you what would happen if the statement were true. It tells you nothing in those vacuous cases where P is false or where Q is false. The sufficient condition is false. So because you don't have that data, you don't really learn that much. Well, the biconditional says, well, I need it to be the case that both if P then Q and if Q then P. So in other words, I'm going to take those last 2 columns that I made, if P then Q and if Q then P. I'm going to treat those like they're statements, which they are, by the way, and I'm just going to use the AND operator on them, and that gives me P if and only if Q, which we do with this double arrow in both directions. Okay, so let's use the AND operator on these 2 columns. Well, true, true, that's a true. True, false. In order for the AND operator to work, I need a 2, so that's a false. False, true. Well, in order for the AND operator to work, I needed them both, and that's a false. And finally, in the bottom, true, true, that's a true. So, P if and only if Q is what happens when they're both false or they're both true. That's when it's true. And it's false if there's a problem in either direction. So we've already identified some really interesting ways to take things that we know and turn them into things that we didn't know that we knew, right? So we can use and, we can use or, we can use not, we can use if then, and we can use if and only if. That's 5 ways to take 2 claims and convert them into a new claim. That's pretty cool. I'm going to revisit statements a little bit later to show you 2 more operators that you can use on statements, but it's going to be a little bit more intuitive for us to do that once we've talked for a little bit about sets. So let's talk about sets. You can usually tell when I'm about to answer a hard question or a question that I don't feel fully equipped to answer extemporaneously when I go to the bottom shelf on the Bookshelf of Awesomeness. So this book was on the bottom shelf of the Bookshelf of Awesomeness. I'm going to put it back and I'm going to get another one of my favorite books off of the Bookshelf of Awesomeness. Let's play some Bookshelf of Awesomeness music. Don't even act like you're not impressed with these shorts. You're like, man, I wasn't expecting shorts that cool. This is another one of my favorite books. Don't get this book. This book is probably a little bit, unless you're a math major or something, this book might be a little bit, this is a hard book. Real Analysis with Economic Applications. This is one of my favorite books. I've never met Professor Oak, but this book is it just makes me happy when I read it. So, what's a set? Ooh. We're not going to be able to answer that all the way rigorously because it's really hard. And for a while, the question about what constituted a set, the fact that some wrinkles in the sort of intuitive definitions of what a set was, those wrinkles created an existential crisis in math for like 5 years or something. This was around the early 1900s. And a lot of this was because of the work of, I need to figure out how to pronounce a name. I think it's Georg, but I could be wrong. Georg Cantor. This is a mathematician working in the 1800s who did work that was so outside of the box foundational that other mathematicians thought it was rubbish, and some of them thought, like, he didn't just catch flack from other mathematicians that thought it was rubbish. Philosophers and even theologians thought that he was full of malarkey. And you're like, what the heck does a theologian have to do with a mathematician? Well, Cantor worked a lot about the concept of infinity, which isn't that hard to think about how that relates to views on the Almighty. And so, Georg Cantor developed this set theory and thought about what it means for a set to have an infinite number of elements. We'll talk about that in a second. But his definition about what a set is it is one thing out of many. And that concept of one thing out of many is so powerful that you don't even realize it. So I could say to you right now, the set of all voters in the United States, the set of all eligible voters in the United States, and without having to access any data, without going to my computer, without calling the government or the census office, I just defined a mathematical object where every element of that set is an individual voter, a distinguishable, I can tell one voter from another. There are formal criteria for what it is to be a voter. I know who's in that set and who isn't in that set. And I just named them all. I just named hundreds of millions of people like that. The set of all voters. I could just as easily have said the set of all coalitions in Congress. And then you're like, well, what's a coalition? Let's talk about the Senate just to keep the math easy. So there's 100 senators in the United States Senate. So if I said to you the set of all possible voting coalitions, that means the set of all one senator together, two senators together, there's a whole lot of these, 3 senators together, 4 senators, all the different combinations of senators. Right? From the 100 ways to have a single senator, to the one way to have 100 senators, to the, I'll work it out, however many different ways there are to have 50 senators. It's a lot. So set theory, when you don't think about it too hard, gives you a way to say, all right, I'm just going to say the set of all somethings, or imagine this as a set, and then you can do all sorts of cool things with sets. So the core idea of a set is that it is comprised of elements. A set is a thing that is comprised of elements, and they don't have to be logically connected, right? So I could say the set X equals mug of tea, dog that I like, and class that I'm teaching, right? So now I've got a mug, I've got a dog, and I've got a class. And you're like, what does that mean? Well, it doesn't mean anything. All I did was list all the elements, right? In game theory, we'll be talking about the set of players. Who are the actors that influence a given outcome? So, for example, in a presidential election, maybe the relevant actors are the incumbent candidate and the challenger candidate. So there's a set with 2 elements, the incumbent and the challenger. In a voting game, it could be that it's the set of all voters, in which case we have 100 million. In international relations, we might be thinking about the set of all possible ways to divide territory between two countries. In which case now that's a huge set, right? So maybe I have 0% of the territory, maybe I have 1%, maybe I have 2%, and everything in between, by the way. 2.9%, 2.8%, all the way up to 100%. So now I've got all these different ways of dividing a pie. That's a set. So sets might be the people that we care about. They might be the outcomes that we care about. They might be the actions available to a player. If you're a soccer player and you're thinking about which way to kick a penalty kick, you go to the left, to the middle, or to the right. Now I've got a set with 3 elements: left, middle, right. So sets are going to be people, they're going to be outcomes, they're going to be actions. The only thing that really matters is that you can list them all whenever you need to, and you can detect whether or not a given object is an element of the set. So for this class, I don't yet know the names of all of you just yet, but I could say the set of all students in this class. And that would be an unambiguous collection of individuals, right? I would be able to work on that set pretty easily. And if you showed me a given individual, I would be able to verify whether or not they were a member of that set. Moreover, for any 2 of you that are watching this video, I can tell one of you from the other, right? There is no confusion about which of you is student 1 and which of you is student 2. So because of that, the set of all students in this class is a perfectly well-defined set. There are some numeric sets that will come up very often that are probably worth mentioning now to give you a chance to see what they look like. So for example, I might choose a set with n elements. I might want the set with the first n numbers. So for example, if n equals 1, then I've got the set 1. If n equals 2, I've got the set 1, 2. If n equals 3, 1, 2, 3, and so on. What's cool about that is I can easily write out a given number and see all of the individual components. Implicit in this little example is I also could have written the set with the first 0 numbers in it, counting numbers. And you're like, what does that mean? Well, that has 0 elements in it, right? It is what we call the empty set. And we denote the empty set with this funny Scandinavian letter. And so this Scandinavian letter, sometimes you see this used for like a null element or something. What that means is that there's a set with nothing in it. You'll see that this is very important soon. All of these other sets had at least one thing in them. 1 thing, 2 thing, 3 thing, 4 thing, etc. So those are all sets. The set with the first 0 counting numbers, the empty set. The set with the first 1 counting numbers, that's just the number 1 in a set. 2, 1, 2. And then you can check, is 1 an element of the first set? Yes, and I write that 1 is an element of that set. Is 2 an element of that set? Well, no, 2 doesn't live in that set. So that's a no. It's a logical statement to say that a given object is an element of a given set. That's either true or false, but not both and not neither, right? So if I say to you, 1 is an element of the set of counting numbers, that is either true or false, but not both, and in that case it happens to be true. If I said to you, -1 is an element of the counting numbers, well, unless you're a very special person that starts their counting with -1, that isn't a counting number, so that is not true. And I can either write that as negate, or I can just put a slash through that element symbol. Okay? 2 little matters of housekeeping as it relates to sets. So first of all, the order that you enumerate the elements of a set in, it doesn't matter. So if I'm listing all the suits of a deck of cards, diamonds, clubs, spades, hearts, I could list that way. I could list hearts, clubs, diamonds, spades. It's the same set. So in other words, a set is invariant to the order that you introduce the elements in. And a set, you don't need to introduce a given element 2 or more times. Once it's in there, right? So hearts, clubs, spades, I forgot. Hearts, clubs, spades, diamonds. You don't need 2 diamonds. That's the same set as the original set 2. It doesn't really matter. So a set is invariant to both order and the number of times that you introduce a given element. And again, just to verify, the statement hearts is in that set is true, and Illini is in that set is false. There are going to be some sets, mathematical sets, that come up often enough that we give them special symbols just to remember them. Probably the single most important of those is the set of natural numbers. Sometimes these are called the counting numbers, and we give it this special N symbol, this double N. It's called the blackboard font, I think. So that N is just the set that contains 1, 2, 3, ... Now look, you're thinking to yourself, how can there be a ... Well, a set is allowed to have an infinite number of elements. In this case, there's an infinite number of counting numbers. 1, 2, 3. You give me any counting number, a Google, which is just a 1 with 100 zeros after it. You give me that, and I could say, +1, and that's still a counting number. So in other words, there isn't a biggest counting number. So that's an infinite set, we call that. But it's still a perfectly well-defined set, the set of all counting numbers. If you gave me a number, I could verify if it was in that set or not. And if you gave me any two elements, I'd be able to tell one from the other. That's all that I needed. So the natural numbers come up pretty often. That's N. The integers come up pretty often. That's all of the counting numbers plus 0, plus all the negative numbers, -3, -2, -1, 0, 1, 2, 3, and then ... in either direction. Those come up pretty often. The rational numbers, this is all the numbers that can be expressed as a fraction of two integers, right? So 1/3 isn't a counting number, but it is a rational number. It's not an integer, but it is a rational number. And then because there are some numbers that aren't rational, like pi or e, other important numbers, we also have devised something called the real number line, and that's this R, and that's just that's all the numbers from, something, it's bigger than -infinity and it's smaller than infinity, but if it's a number that lives in there, be it a rational number, an irrational number, positive, negative, integer, non-integer, counting number, non-counting number, basically all of the numbers live in R. So that is a very important set for us. We'll be using it very often. There are times where we want to say all of the positive or non-negative real numbers. Like you might just want to say, minus signs are hard to keep track of. And then we'll use R plus and R plus plus, and those will mean all of the non-negative reals and all of the strictly positive reals. So if I say to you that X lives in R, that's a way of saying that X is just a real number. So how do we specify a set? How do we name a set? Because it seems so easy. I was just saying, the set of all voters, boom, it's a thing. Well, it's a little bit more complicated than that. So let me try to be a little bit more precise. So in many instances, it's possible just to list all of the elements of a set. We just went through some of that. So for example, with the natural numbers, I can just list 1, 2, 3. I put them in these squiggly braces, and that's the way of writing that this is a set. And then the ... is the way of writing to somebody, and you keep going in the same manner that you would have inferred from the process 1, 2, 3. So just simply enumerating the elements of a set, oftentimes that's the easiest way to say what a set is. So for example, let's say that we wanted the set of all instructional staff for this class, right? Then that set would just be Sang-hoon and Rob, and that's it. So for finite sets in particular, this is very easy. If I wanted to list all 50 states, right, then I might go Alabama, ... Wyoming. And the fact that it ended with a given element sent you the signal that it's a finite set. It has a stopping point. And then the ... it wasn't even like a and so on and so forth. It was just a way of saying, okay, you can look up the rest, right? You can look up the rest and if you figure that out, then it's fine. But oftentimes we're interested in these sets for conceptual reasons rather than just it's fun to enumerate all of their elements reasons, right? So if I want to say to you the set of all voters, like we did before, how would I write that? Well, the first thing, if I want to maintain good practice, is I define a big set that's sort of like the universe of discourse. So the first thing that I'm going to do before I say the set of all voters, well, implicitly voters are human beings, right? Let's say that X, my universe of discourse, is just the set of all individuals living in the United States. Great. Now I have I'm defining things with respect to this sort of world that I've created. It's a good place to talk about who's a voter. It's a bad place to talk about intergalactic scale, right? But now that I have that universe of discourse, it's very straightforward for me. So I'm going to use something called set builder notation, which is going to involve, instead of listing all the elements, I'm going to say it's the set of all somethings such that a property is maintained. So let me give you this example. So if I wanted to list the set of all possible voters, I'll still use the braces. This is still the nice way to send the signal that this is a set. And I'll say it's the set of all little x's in big X. It's the set of all individuals. So when I say little x in big X, I said that X was the set of all individuals. So it's the set of all individuals such that, and in order to send this such that signal, I'll use a colon or a pipe. And then after, I can write, even just in plain language, X is a registered voter. And I just did it. We took the set of all 375 million individuals that are living in the territory of the United States right now, and we just honed in on the set of all registered voters, right? And so you might have enumerated all hundreds of millions of them, and that's the same set. Even though you did all that legwork, it's the same set, right? It's really elegant when you think about it. It's almost problematically elegant sometimes, but we won't worry about those wrinkles too much. So a set is usually defined with respect to a universe of discourse. If it isn't, problems can arise, but nothing too big in our context. Now again, it's not super duper interesting to just talk about a set without combining it, right? So we're going to want to combine sets. The most obvious example is we're going to want to try to, if I can go to the left or to the right, and you can go to the left or to the right, we need to think about the set of all possible left-right combinations, right? We need to think about all the possible, these are called strategy profiles, we'll talk about it in a few weeks. So we need to find a way to make a set out of some other sets. The same way that we just made statements out of other statements. It's actually the same exact process. Well, if I wanted to do that, I need some operators, right? I need something that takes one set, we'll call it A, and another set, call it B, and that makes another set out of them. Well, as you might imagine, the operators are going to look very similar to what we used with statements. I'm going to need to go to the board again. Zink, zink, zink. We're at the board. I'm going to use a tool called a Venn diagram to convey some of this to you. The first thing that when I draw a Venn diagram is I'm going to draw the entire universe of discourse, X. So everything is going to be part of X. And I'm going to introduce these two sets, A and B. And these will both be parts of X. I haven't yet introduced the term I'm going to use for that. So if I want to make a new set out of A and B, well, one way I could do it is the set of all things that are in A and in B. This is called the intersection of two sets. And the notation that we use for that is this rounded wedge. So what used to be a wedge is called cap in LaTeX, but right? So if I write A intersect B, that means the set of all things in X such that it's in A and it's in B. And the word and was in there. I said and. So I took the two statements, X is part of A and X is part of B. I linked them with an and I used that to define the intersection. I could also use the or operator, right? So I can think about the union of two sets, which is the set of all things in X that are either part of A or part of B, or both. Remember, this is an inclusive or. And so that ends up being this entire trace. So the intersection was this lens of an intersection, literally an intersection at that point in time, of these two circles. Conversely, the union is just everything that's covered by at least one of the circles. So and goes to intersection, or goes to union. Where does not go? Good question. Well, it's going to go to the complement of a set. So when I write the complement of A, that's the set of all things in X that aren't part of A. So visually, that winds up being everything around A, but not A. So consider two sets, A and B, that don't overlap, right? Which is to say there's no elements in A that are also elements of B, and there's no elements of B that are also elements of A. Think about the intersection of those two sets. So the intersection of two sets that don't touch, right? That's the set of all things that's in A and in B. Well, we just said that there's no such thing. We refer to these two sets as disjoint or mutually exclusive, right? So the idea here is that it's impossible to both be an A and a B given the way that A and B have been defined. If I gave you the set of all democracies and the set of all autocracies defined by the Polity score, and say, well, take the intersection of them, find me the set of all countries that are both democracies and autocracies, that would be the empty set. There is no such country. So the empty set is going to play a really big role for us because it's a good way for us to verify that two things are mutually exclusive, two things are disjoint, two things can't happen together. Okay, so we've converted and, or, and not into this set sort of language. And we are seeing that sets are defined in terms of statements. You could also define statements in terms of sets. And so there's this intimate circular relationship between sets and statements. And so it's really just two sides of the same coin. Let's talk about a very important term in the context of sets. So sometimes we worry about whether one set is in a sense smaller than another set. What would it mean? Well, there's a lot of different things that could mean, but the thing I have in mind is that one set is smaller than another set if every element of the first set is also in the second set. So consider, for example, the sets x equals 1, 2, 3, and y equals 1, 2. So one of them has 3 elements and one of them has 2 elements, and in a sense that means that the first one is bigger than the second one. But it's also true that every element of set y, 1 and 2, is also an element of set x. That means that y is what we call a subset of x. And we write that y subset or equal to x. It kind of looks like less than or equal to when you think about it, right? And it kind of means something similar. It's a way of ordering sets. Now that equal to part, in this case, it isn't possible that they're equal because they're not the same set, right? So the reason they're not the same set is that there's an element in the first set, namely the number 3, that isn't part of the second set, right? So they're not the same set. Two sets are the same only if they have the same exact elements. So in this case, not only is y a subset of x, it's a proper subset of x, which means that you can actually put a little slash through that equal part. And that's a way of saying y, everything in y is part of x, and there are things in x that aren't part of y. In fact, strictly speaking, two sets are equal. The way that you show that two sets are equal, which you won't have to do, is to show that the first is a subset of the second, and the second is a subset of the first. When you think about it, subsets are sort of related to implication. So if I said to you, if a student works hard, then they will get a good grade. What that means is that every student that works hard will get a good grade. Now, there might be ways to get good grades that don't involve working hard. Maybe you're a prodigy, or maybe you cheated, or maybe you got lucky on every problem set, or whatever. I have nothing to say about that in my claim, if you work hard, then you'll get a good grade. There are other ways to get a good grade that don't involve working hard, but I'm not talking about that in this claim. So what I'm saying is, the students who work hard are a subset of the students who get a good grade. Whoa, that makes sense. Let's think about that in the context of a Venn diagram. So a proper subset is a set that lives entirely, so I could draw one circle and then have another circle that was entirely part of it. And for a proper subset, it has to be fully consumed and not just the exact same thing. So this subset relation is actually a nice way to think about implication, and it helps you to visualize some of the differences between if-then and if and only if. If and only if means that the two sets are the exact same thing. And if it's if-then, but not if and only if, then there's a proper subset picture happening. One other really important way for us to define a new set out of some other sets is to appreciate the fact that order can matter. So in the definition of a set, we don't care about the order of the elements, right? So we said that hearts, clubs, diamonds, spades is the same as spades, clubs, diamonds, hearts, or any other order of the four. As long as it's the same four elements, the order doesn't matter. But sometimes the order does matter, right? Or there are just some situations where we think we want to know one thing first and then a second thing second, right? So you might want to know a city name and then a state name. Urbana, Illinois. Urbana, Ohio. So in cases like that, we need to think about the set of all possible combinations of two sets. We call that the Cartesian product, or just the product sometimes. And you use a times symbol in between two sets, like A times B, in order to denote that. And so the Cartesian product of two sets is just the set of all ordered pairs. So if I have A and B, then the Cartesian product is the set of all A-B combinations, right? So you're probably used to the plane, the two-dimensional plane. You probably talked about this in high school, right? There's an x-axis and a y-axis. Well, when you think about it, that's actually just the Cartesian product of two lines. It's the set of all possible pairs of numbers, where the first number tells you how far left or right you are, and the second number tells you how far up and down you are. Latitude and longitude are just two numbers that tell you how far you are on the east-west and how far you are on the north-south. So these Cartesian products are going to be very useful for us. Essentially, a Cartesian product is a way of saying, tell me all possible combinations of two sets. It's really easy to visualize this. So for example, let's say that I had the Cartesian product of 1, 2 and AB. Well, now I've got four possible elements, right? I've got 1A, I've got 1B, I've got 2A, and I've got 2B. So I took these two sets where they each had two elements, and you can quickly sort of draw out the set of all combinations. And really, the visualization is no more complicated than it was for you to take one real line and cross it with another real line and make a plane. Just for a slightly more complicated example, let's suppose that A is the set of all suits in cards, right? So spades, hearts, diamonds, and clubs. I think I said that right. So there's four elements. And let's let B be the set of all denominations on the cards. 2, 3, 4, ... 10, Jack, Queen, King, Ace. Right? So there's 13 different denominations of cards. So then if I took the Cartesian product of all the suits and all the denominations, well, then I'd have 4 times 13. I'd have 52 different kinds. I'd end up with the 52 cards of the deck in this Cartesian product sort of array. So whenever I write out the Cartesian product of two sets or more sets, I can keep the process going. So I can take 3 real lines and make space, right? I can take 4 real lines and make space time. So I can keep going as many times as I would like to, because in the social sciences, oftentimes things are very multi-dimensional. Fine, keep going. Just keep adding real lines. Cartesian product over more and more sets. That's not too big of a deal. But oftentimes we'll be interested just in 2 sets. You'll see. So the Cartesian product is a really convenient tool for us to make ordered pairs out of 2 sets. To say, give me all the combinations of 2 sets. Oftentimes we'll use an indexing set to list all of the relevant identified individuals within a given set. So for example, I might use an indexing set to talk about the set of all students in this class. So then I can choose an arbitrary student in this class and say, well, they're part of that index of students. So that index of students has something like 80 or 90 students in it. After this lecture, we're probably down to 10. Right, so I have this index of students, and then I can say, well, for every student in that indexing set, they're enrolled in this class. So these indexing sets are going to be a really useful way for us to use subscripts and superscripts and whatever the case to say the same logical point, the same property applies for every member of a given indexing set. You're probably a little bit confused by that. Let's go back to statements as promised, and I'll show you how that works. Okay, so we're back at statements. Now suppose that I made the following claim, which I'll teach you how to encode here in just a second. But suppose I said, every student in this class is a political science major. Okay, that's a logical statement. That's either true or false, but not both. Every one of you has a major. It's unambiguous. You might have multiple majors, but let's say that you're a political science major if any of your majors is political science. Great. So what I'm saying is, for all members of the set of students, right, for you, for your best friend in this class, for somebody you don't know, for every one of you, beep, I'm making the argument. My statement is not about one of you. It's not about two of you. It's not about five of you. It's about all of you. So I needed a set to say what all of you is, an indexing set of all the students in this class. Let's say the indexing set was n. For all of the n students in this class, or capital N is you, somebody else, ... everybody in this class. For all I in n, student I is a political science major. That is a statement where now it's not two statements I'm combining, it's a whole bunch of them, right? And what I'm saying is, for all of those, for all of you, you're a political science major. Okay. So the way that I say for all is I would say upside down A. That is called the universal quantifier for all. That's the sixth thing that we needed to encode in terms of logic, for all. Now, you can imagine that there's other ways to quantify the number of things that a property holds or doesn't hold for. And the other one that you see a lot is there exists at least one, or just there exists. So that's an upside down E. Yeah? And so I read that there exists. So let's suppose I want to say there exists at least one student in this class that is a political science major. So I would say there exists I in n such that student I is a political science major. Great. So now we've got 7. These are all 7. And, or, not, if then, if and only if, for all, and there exists at least one. Where for all and there exists at least one are defined with respect to some set in question, some indexing set. Okay, so let's think about negating. What does it mean to be false? So consider the claim, which is probably false, that for all students in this class, student I is a political science major. Some of you aren't political science majors. Welcome. So what would it mean for my claim to be false? It would mean that for at least one student, that student isn't a political science major, right? So the opposite of all of you are political science majors is not all of you are not political science majors. The negation of that is for at least one of you, there exists some student J in N such that student J is not a political science major. So in other words, to negate a for all, I use a there exists. That's heavy. Now suppose that I said, there exists a student in this class that is not a political science major. What would it mean for me to be wrong? Well, that would mean that for every one of you, you're not a political science major. So to negate a there exists statement, I use a for all statement. So if I say, for all I, P is true, the negation of that is there exists at least one J such that P is not true. You'll have a chance to do this on your problem set. And if I said to you, there exists at least one I such that P is true, the way that I would negate that is to say, P is not true for all I. Once you get used to it, it's going to be like super duper simple to you. But people get this wrong on a day-to-day basis. We call that cable news. Now, once I have an indexing set, it's actually very easy for me to repeat some of the operations that we've talked about. So you've probably seen like a summation operator, the big sigma, and that means take everything given an index, right? I equals 1, 2, 3, ... n. So for all the indexed elements, add them up, right? There's also products, for all of them, multiply them. And several of the operators that we've talked about have big versions to keep notation a little bit simpler. So suppose that I had a bunch of statements, P1, P2, P3, ... Pn. So I'm indexing my statements with this subscript, okay? So suppose I had that. I wanted the statement, all of these are true, right? In other words, P1, wedge, P2, wedge, P3, ... wedge, Pn. Oh my God, that voice is so awful. Wedge, wedge, bingo, we have a bingo, bingo. That was like most of my childhood with my grandma. Back in the old day, grandmas used to take their grandkids out to gamble on Thursday nights at bingo halls. That's how I learned how to do math. So I don't want to have to write out all of those. So instead, I can use the indexing set and have a big wedge, and it's wedge I equals 1 up to n of P sub I. Easy peasy lemon squeezy. I can do the same with the OR operator. Likewise, suppose that I had a bunch of sets. A1, A2, A3, ... AK. Okay, well, I can take the big intersection of them. Same, there's a big loopy wedge, I equals 1 up to n. Or I can take the big union of them. And basically, these relate to there exists and for all, right? So with big and, for example, what I'm saying is PI is true for every one of these statements, right? So the big wedge is true only when it's true for all. And with the big OR, it's true only for at least one. So if there exists at least one statement that is true in this set of statements, then the giant OR will be true as well. And similarly for the sets. I know this seems complicated, but really all that we've done is talk about sets and how to make many out of one and one out of many. And we've talked about 7 plain language terms from our everyday indexicality-laden language, the sometimes ambiguous language, and we've figured out a way to encode them in unambiguous ways that a computer wouldn't blow up at us. Great. Well, you've been promised 3 things, so in the C block, we're just going to briefly talk about what a function is and how it maps 2 sets. So you've probably worked with a function before. You've probably seen f of x equals x squared minus 9x plus 2, right? What is a function, though? A function is more than just a way to take one number and turn it into another number. That's what I just described to you, right? It was like a cookbook. So that equation was a way of saying, take one number, do a couple of things to it, and it becomes another number. It's a recipe, right? But there's more to functions than just this recipe, algorithmic, computational thing, right? So A function can be so much more than that. Broadly speaking, what a function is a rule for taking elements of one set and taking them to another set. So whenever I talk about a function, and we're going to be talking about functions a lot in this class, utility functions, we're going to be talking about expected utility functions, we'll be talking about belief functions, best response functions. There's all sorts of functions in game theory. So what's a function? Well, it's not to undercomplicate it, but it's just a way to draw arrows from one set to another. So whenever I talk about functions, I think it's really easy to draw a set as a blob. I think a set is a blob with dots in it. Okay, so here's one set. I'm going to call it A. And it's got these dots in it. Okay? Every dot in this blob of dots is an element of A. I'm going to draw another set. I'm going to call it B, and it's got dots in it. Blobs and dots. You're paying good money to learn about blobs and dots, but it's actually very profound. Easy for me to say. So what's a function? Well, a function is a rule for taking the dots in one blob and sending it to dots in the other blob. So in this example, I might just take a bunch of arrows and it takes each dot in set A to a dot in set B. It doesn't always have to be the same a different dot. It can be the same dot. It doesn't have to be different, whatever. The only rule is that every element of A has to be sent to B and has to be sent to only one part of B. So I'm not allowed to send any element of A to multiple elements of B. Every dot in A goes to one and only one dot in B. Not 0, not 2, one dot. That's what makes a function a function. What makes a function is that it goes from one dot to another dot, not 2 dots, not 0 dots. So let's consider an algebraic example again. So if I said to you, f of x equals x squared. Implicitly, you know that that's about real numbers, right? So x here is a real number. And so the idea here is that this function f reads in a real number, x, and it spits out another real number, right? So it takes 2 and it spits out 4. And it takes -3 and it spits out 9. And it takes the square root of 2 and it spits out 2. So the idea with f of x equals x squared is it's a rule that reads in one dot, one number, one real number, and it spits out another real number. So in other words, A is my fancy R and B is my fancy R in this example. We're going to call, whenever we write down a function, we'll call the input set the domain, and we'll call the output set the codomain. So in this abstract example, A is the domain and B is the codomain. Now, the clever people among you might be thinking, well, it's impossible with our real numbers, just basic real numbers, to have a negative squared number, right? So any number squared is positive. -1 squared is +1. -2 squared is +4. So, given that, is our codomain really the reals? Well, maybe not. It doesn't have to be. You can have a little bit of ambiguity with how you define a codomain. The set of all numbers that actually get hit by a function, the set of all output elements that actually get hit, that's called the range. And that might be a term that you're more familiar with. If the codomain is equal to the range, that's especially pleasant, but it's not a super huge deal. So all that a function is a rule for turning one dot into another dot, which is great because we're going to be doing this on things other than numbers, right? So suppose that the domain of my function is a set of things I can choose from. It's a menu. Suppose that I go to Black Dog. I go to their website because I'm not going to eat in Black Dog right now. But if I go to Black Dog's, it's a barbecue. If I go to the barbecue takeout website, there's all sorts of delicious meat for me to choose from. now I'm thinking about it. Oh God, the burnt ends. Oh, if you're not in Champaign, Urbana right now, the next time you're here, go get and if you don't mind eating barbecue, get you some burnt ends. Oh my goodness, it's so good. Anyway, so I have a menu. On that menu, there's burnt ends, pulled pork, brisket, chicken, all the different barbecue options. So let's say that X is the set of all barbecued meats available at Black Dog Barbecue. This is my favorite set. So imagine that's my domain. Now I need to specify how happy I get when I eat them. So maybe I'll assign every one of those a number that indicates how much I like them. Maybe my favorite gets a 10, my next favorite gets a 9, my next favorite gets an 8, right? So this, my utility, my bliss from consuming these things is captured by a function that reads in meat and spits out happiness numbers. And you're like, that sounds stupid. It kind of is. We're going to talk about this in excruciating detail next week, so it's really good if you get an abstract sense of functions now, because a utility function, all that a utility function is a rule for taking alternative and spitting out happiness numbers. There are special kinds of functions. So if every part of the domain, if every dot in the domain gets sent to a distinct dot in the codomain, which is to say no two dots go to the same dot, no two A's go to the same B, we call that function one-to-one. In other words, each A gets its own distinct and unique B. That's a one-to-one function. And we call a function onto if every element of B gets hit by some A, right? So this codomain range thing gets relevant. So a function is onto if its codomain is exactly equal to its range. But really, if every dot in the B blob gets hit by some arrow from the A blob, then it's onto. So sets, functions, logic. These are going to be the core backbone sort of skills. This is the invisible background. This is the set of physics that we won't even talk about. In week 12 or 13, you might be thinking to yourself, man, I don't know why we did week 1. And that's just evidence of how foundational these things are, because they structure your thinking in such ways that you don't even notice them eventually. And so if you get pretty good at just thinking in terms of sets, functions, and logic, if you get good at these things, you'll be prepared for whatever's coming, this class or otherwise, because this is just an organized way to keep your thoughts in one place without going insane trying to keep track of them all. And I think that that's why we use mathematics in the social sciences. To the best of my knowledge, we're not trying to derive law-like regularities the same way that the usual picture of the hard sciences works. We're just trying to keep our thoughts organized, right? We're just trying to make sure that the machine works internally. So I want to leave you with 2 provocative thoughts about mathematics, or I find them provocative anyway. The first is, there was a long time where if somebody asked you for a definition of mathematics, the only way that you could define it, given how many disparate things seem to be involved, is what mathematics is what mathematicians do for a living. And that's not a great answer. It's a little bit tautological. Instead, I think a really great definition of mathematics, which there's a set of papers on the subject, and this is advanced by Devlin in the book that I've shown you before too. Math is the science of patterns, right? So algebra and number theory, that's the science of patterns that emerge in counting. Geometry is the study of patterns of shape. Calculus is the study of patterns of flow. Probability is the study of patterns of chance. Then what's game theory? If it's a branch of applied mathematics, albeit a small and not super duper important one from a mathematical standpoint, then what is it? Well, it's the study of patterns of strategy, patterns of strategic interdependence. And so, if that's the case, then we can view these tools that we're devising as components in trying to figure out these patterns, but you can only identify patterns if they're part of a well-defined frame of reference, right? So if I showed you a bunch of random noise and said, find a pattern, you might be able to find one, but it would be easier if you found a way to array them in such a way that the pattern became obvious, right? And that's sort of what we're looking for here. And then you might well be wondering, well, why would you do mathematics? Why do we need to know, why do we need the science of patterns? Why do we need patterns? And the answer is because it makes things that were otherwise invisible visible. The differential equations that an aeronautical engineer uses to model airflow makes obvious the fact, once in the context of the model, that an airplane could fly. Now, that's not visible to us with our eyes, right? Only through the power of a model that captured patterns of airflow were we able to see the invisible thing that a giant, heavy metal airplane could fly. This raises the question, what's the invisible thing in political science? And the answer is, get creative, guys. I mean, there's so many things that are invisible that we're able to detect. Subtle little shifts in incentives and how they shift behavior, all the costs and benefits of various actions. We can predict voting patterns with some regularity, not because it's obvious to us on a sensory level, but rather because these mathematical models that we've built, be they theoretical models or empirical models, statistical models, these models and the associated mathematics, the associated science of patterns, help us to see things that were invisible. In the case of game theory, what becomes visible are the endogenous responses, the inherent strategic choices that individuals or groups make in these invisible cost-benefit analyses that they're doing. So that's provocative thought one. Math is the science of patterns, which means that game theory is the science of patterns of strategic interdependence, and it makes visible the invisible incentive structures. Provocative! 2. Is mathematics invented or discovered? That's heavy. If these are all tools that we're using to keep our thoughts organized, then very much it's invented, right? But there are things that we learn as consequences of the system that we build to keep our thoughts organized. There are implications, right? And so it is also discovered, right? So we come up with axioms that we think seem to serve us well for a particular context, maybe geometric axioms like Euclid used, or maybe behavioral axioms that we'll be imposing next week. And these axioms have all sorts of implications. And so we invent math in the sense that we design tools to solve particular problems for us, but we also discover math in that the tools that we design have unintended far-reaching implications that we have to accept as true because they're part of the system that we're developing. So actually, I use the verb twice here. I don't think mathematics is invented or discovered. I think it's designed. And that introduces interesting questions about what are the design problems that we social scientists face? What are the problems that we would like to design mathematical solutions for in the context of strategic interdependence? And when you think about it that way, it's a little bit more obvious why we would need these foundational tools of sets, functions, and logic, because they're going to be the building blocks of all of these solutions that we try to design. Thanks for watching. I can't wait to hear what you think about the problem set, and if you have any questions about the lecture, be ready with those too.